Okay, so let's consider something moving vertically or, up and down. Um, for argument's sake, let's say we have just something tied to an end of a string. And the tension in that string is 80 newtons. And the mass that's hanging on the end of the string is 10 kilograms. And so the question is going to be, well, what's going on with the motion? It's a little more vague. It doesn't tell us if it's in equilibrium. It does not tell if it's accelerating. It doesn't tell us a lot of things. But because we do have the forces, we have enough information to tackle this question. And as always, the first thing we're going to do is do a free body diagram of the object. So we do the free body diagram. We have the object, and we have a tension to deal with. And that tension is through the eyes of the box, through the eyes of the mass. Well, that tension is the string, and that's trying to, prevent us from falling, right? If there were no string, the object would fall straight down. But since there is a string, the object is prevented from falling. So the string actually holds the object or supports the object upward. So that tension is going to look like that, right? The string is pulling on the box, prevent it from falling, or preventing it from going in a free fall. We always have gravity. We assume, unless otherwise stated, um, that we're on Earth and that there's weight. What a lot of students are going to put here, which is, I guess I know why they do it, but they always think that there's some kind of normal force. And there isn't a normal force. This is not resting on a surface. So if it's not resting on a surface, there's no force between surfaces. There's no interaction there. And so there is no normal force. So please don't add a normal force when one does not exist. Okay? Um, and we know these values. We know this is equal to, oopsie, we know this is equal to 80 newtons. That was given. And the force due to gravity we don't know offhand, but we can figure that out, right? Because we know force due to gravity equals m times g. And some people will calculate it off to the side, and some people will wait and put it in the formula later. But it's interesting to see what's happening here. Well, we can ask ourselves, well, are the forces balanced? They're definitely not balanced. We can also ask, well, then if they're not balanced, which direction is this thing going to move? Which direction is this going to accelerate? In this situation, it's accelerating downward. It's pretty clear to see that the 80 upward is not enough force to support all of the 98 newtons down. So this thing is going to pull down and be pulled down slowly. The acceleration is going to end up going downward. Now, you're like, well, wait, but there's an upward pull. I know, but that upward pull is not enough to overcome this downward pull. So it's going to slip downward. It's not going to go into free fall, but it definitely is moving downward at a slower rate than free fall. So the question is, well, how much acceleration is that? Well, we can do the formula. We know the summation of the forces in the y direction equal ma now. We happen to know that there's a positive tension, because again, we typically make up positive. And we have our gravity acting downward. And we know that's equal to, again, ma. Those forces will be related to that mass and acceleration. So 80 minus 98.1 equals 10.0 a. And if I do the subtraction, I will get negative 18.1 equals 10.0 A. And so A is, and I really should, wow, put units, or 1.81 meters per second squared downward. So that's the acceleration going on. And of course, in other problems I could ask part B, part C, how fast is it going after 3 seconds, and so forth. But I just wanted to illustrate a vertical problem like this. We'll talk about more other types of vertical problems called apparent weight at a later date, but this is enough for now. Next set of problems, we're going to start working things at angles. Fun times.